Hey everyone, today I'm going to be showing you how to use the two Excel documents that I provide in order to calibrate your detector. So if you don't already have these two Excel documents that I'm talking about, feel free to shoot me an email and I'll be more than happy to send them to you. Even if you don't own a detector, I'd be more than happy to send these to you. So I've been getting a lot of requests for a video like this just to show the specifics of the Excel documents so that you can have a sort of a better handle on how to use them effectively. The first document that I want to show you is this alcohol standards calculator document. You know, there's relatively simple math that you can do to calculate dilutions, but I still use this Excel document to calculate mine just because it takes a lot of the guesswork out and a lot of the self-doubt out about the math that you do to calculate these dilutions. So you can use just about any alcohol to dilute down to your standards, but I would recommend at the very least getting a plain alcohol like a vodka would be really good. So what we have here is our desired alcohol percentages. So you can change these. So I made these pink cells, ones that you can change. And then this next column is the alcohol percentage of the alcohol that you're diluting. So in this case, it's probably something like an 80 proof 40% vodka, but you could also change this and make it a 100% ethanol if that's the stock solution that you have. But let's stick to the 40% solution because I think that's what most people have in stock. It's pretty easy to get at liquor stores. So we say, okay, we want 0.1% alcohol. We're using 40% alcohol to dilute. These blue cells you don't need to edit. And then we have this last column that you can edit, which is the volume that you want to obtain at the very end. So in this case, it's half of a liter or 500 milliliters. I would recommend preparing at least a liter of each of your standards. When I do these calibrations, I make sure to make a whole gallon at once because the larger volume that you're working with, the more likely that you'll be accurate with your measuring. If you're trying to measure a very, very small volume, it can be really difficult. But if you're measuring a relatively larger volume, then it's much easier and you're more likely to be accurate. So let's change this to 1 liter, which is 1,000 milliliters. And you can type them all in, but a little Excel shortcut is if you click and drag this bottom right corner, you can just make all of these cells 1,000 milliliters. So then these final two columns are sort of your answer, if you will. It tells you exactly how much water you need, and it tells you exactly how much alcohol you need. So this first column will be the required milliliters of 40% alcohol to make 1 liter of 0.1% alcohol, right? So then you'll also need 997.5 milliliters of water to top that off. So then for the next solution, what you would do is add 6.25 milliliters to 993.75 milliliters of water. And then just one more example that's maybe a little easier to think about. This one would be 50 milliliters of your 40% ethanol added to 950 milliliters of water. That's all of making the calibration solutions. Again, what I would recommend is taking your large volume of calibration solutions and storing them in the refrigerator to recalibrate your detector whenever you need it. I would recommend recalibrating your detector, meaning make an entire new calibration curve once or twice a month. So that's it for this document. The next document that I want to show you is the actual calibration. So again, we have this sort of color coding scheme. The blue cells, I say, are what you have to change in order to get your results. And the green cells can be changed if you want. So I've had some brewers that want more accuracy in the lower percentages, so they exclude these 2% samples, or brewers who just want more accuracy in general and want more confidence in their test results, so they have more steps of alcohol percentages. So like in the last Excel sheet, there was a 0.75% sample. So if you want to do that, you can change that as well. So what you're going to do is first I'm going to pretend that these data are not there. Originally, you're not going to have any raw readings. You're going to do each sample in duplicate, So you'll take your 1 liter of 0.1% alcohol standard and pour about 25 milliliters into a clean test tube. And then once the detector is warmed up, you screw the sample in and you get a reading. So in this case, you get 243. So what this means is, one very important thing to note when you're using this method is that you do not look at the alcohol percentage on the screen of the detector. You don't use that at all for this calibration method. You're only looking at what I like to call the raw reading on the right side of the screen. So it'll say alcohol, and then it'll say the percentage, and then it'll have a slash, and then the raw reading is right there. So don't look at the alcohol percentage reading on the screen of the detector at all when you're doing this method. You're only looking at the raw reading on the right side. And you don't need to go out to, 2 more decimal places after this. You only need the ones place really, because that's sort of all of the resolution that you're going to get. So you've done your first sample, you screwed it in, the reading was stable. It might have been bouncing around from 240 to 245 and then 243, you assume that it was at 243 for the longest, so that's the number that you use here. Then you unscrew that sample. Ideally, you screw in a sample tube that just has water in it and let that bubble for maybe 30 seconds. If you're lazy, you can let the detector sit just for 30 seconds or a minute until the readings fall a significant amount. So in this case, I would probably say that falling a significant amount would be going down to about maybe 180 or something like this for this number here. That's just what I would assume this detector would fall down to, but just use your best judgment. And then so you pour out your old 0.1% sample that you read already, and then you pour in some new 0.1% standard from your liter stock of calibration standard. You screw this back into the detector, and you wait again until the reading stabilizes. This time it bounces from 245, it's at 245 for a minute, and then it goes up to 250, and then it goes to 251, and it stays there for a second, and it goes down to 250 again, and it goes back up to 251. You get the point. You can just say 251. That's safe enough. And this variability, you don't want to let this influence your judgment. So what I mean by that is you might say, oh, well, I got 243 the first time. That means that this 251 reading is wrong. That's not necessarily the case. Especially your first reading might be a little bit lower than it should be. Your first reading of the day of the detector might be a little bit lower than it should be. There's also several other factors. If you screw in the tube properly, or if one sample was slightly warmer than the other. But the idea of using this method is that all of those inconsistencies will average out. So if you have, sort of a bias to say, oh, well, it should have been 243, but I got 251, then you may be adding some error into the estimation. So, just take the reading that the detector says and build your whole calibration curve. And if something looks funky at the end, then you can go back and say, okay, maybe this was wrong, or maybe that was wrong, or maybe I need to email Nick, whatever. But everything should go relatively smoothly. So you go again, and now you dump out your 0.1% sample, you get a liter of your 0.25% sample, and pour in, between 20 and 30 mils, screw it into the detector, wait for the reading to stabilize, and now you get a reading of 346. Okay, just real quick, one thing that happened here is that when I moved this data over here, it also moved the selection area for the graph. So let me show you this again. So if you have no data in here, it will just look blank. And then as you start typing in the data, you should start getting more points appearing in the graph. Pretend I'm actually getting this data right now. This is data that I got from another detector that I calibrated in the past. Okay, so you've now tested all of your samples and you have a nice curve. And a few of the things that you should be looking for let's mess these numbers up real quick just so that we don't have any bias going on here. A few of the things that you should be looking for first, once you generate all your data, specifically after you generate all of your data, not during, not before, is you should be looking for this curve that goes through most of the data points. And if it looks good, then it probably is good. And then another sort of concrete way to say that your data is good is looking at this R-squared value. So this R-squared value gives you a sort of rough idea of the quality of the line going through the data points, how well the line through the data points matches the actual data. So in this case, 0.99, so you see this E -1, that means you move the decimal to the left 1. So this R-squared is 0.994. That's really, really good. If you have 0.99, that's fantastic. You're doing great. If you have 0.98, 0.97, you're probably pretty good. If you have 0.93, you might have a little bit of issues going on. And if you have something like 0.89 or something like that, you might want to check a few things, make sure the temperature of your calibration standards were consistent, make sure you were testing your samples consistently. There might have been something going on here if you get an R-squared of 0.89 or lower. So those are your sort of first indicators as to whether you built your calibration curve correctly. So if you sort of pass those tests, then the next thing that you can do is take this data here, which is the equation for this curve on the chart, and you're going to type in these constants. This right here is what I call the exponent, right there. This right here is what I call the coefficient. So again, this E -11, that means you're going to move the decimal over 11 times. And so the first one moves past the 2, and then you need to go 10 more times. So that would mean you have a decimal point, 10 zeros, and then 2619. And then this exponent, you have E plus 0, 0. That's just E plus 0. So your exponent is just going to be 3.154. So now we can take those numbers and we can type them into here. So again, our first number was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, 2619, right? And then our exponent, remember, is 3.154. So now what you can see is the prediction, the error, and the percent error have all updated. So the prediction is taking your raw reading that you got when you read your detector, plugging it into the equation of this line, and then giving you what this line would have predicted. So in this case, if you had already built this calibration curve and you got 243, then your prediction would be 0.09%. So if these are decently close to your actual values, then you're pretty good. And the error sort of gives you an idea of that as well. The error is just subtracting this value from this value. So the prediction minus the actual is giving you your error. So in this case, it would have predicted that your 2% solution was actually 1.87% in this case. And so that's an error of 0.13%. And then your percent error, in case you're curious, is your error divided by your actual. So if your percent error is less than 20%, you're doing pretty good. If your percent error is over 20%, your R-squared probably isn't very good either, and your curve probably looks funky, and you might have some data points that are sticking out. And then the final thing that you can do is you have this calculator down here, which is super convenient. So say you have a kombucha sample, you've made sure that the temperature of your kombucha sample is the same temperature as the calibration standards that you used when you made this curve, and you screw it into the detector, and you get a reading of 375. It will automatically tell you the alcohol percentage of your kombucha after you type in the raw reading that you got when you tested your kombucha. You know, it's exactly like it says. It's a calculator. You type in the raw reading that you got for your unknown sample, and then it tells you the alcohol percentage that your curve would have predicted. So a thing to note is you can directly look at, okay, here I have a prediction of 0.34%. How accurate is that prediction? This is very, very transparent since you've created your own calibration curve, and you can go back and look, well, okay, within my samples of around 0.34%, which I think is safe to say between 0.1 and 0.5, the largest error that I have is 0.04%. That's the largest error that I'm getting. So I would anticipate that probably the largest error I can get in my readings within this range is probably plus or minus 0.04%. So you can look at this and say, yes, my kombucha is probably below 0.5% because even with the error accounted for, the highest alcohol percentage this could be is 0.38%. Now, you know, nothing is certain. There's a million different things that could go wrong. You know, the temperature of the kombucha may have been off, or the sample tube may not have been screwed in enough, or you know, there's a million different factors. So no detection method is perfect, but hopefully this gives you a really good idea of the accuracy that you should expect within a certain range. An additional thing that you can do to improve the accuracy even further is change the data that you use. So say, for example, you don't care about 2% alcohol content. Everything that you test is well below 1%, and almost everything is below 0.5%. So you don't really need to know what's going on in the 2% range. So here's what you can do. This is a really, really, really useful thing that I've found to really drastically improve your accuracy in the lower percentages. So if I click on one of these data points, on one of the data points, not on the line, you can see the data selection areas. What you can do is click and drag this bottom right corner up, click and drag this one up, and then it's selected a different area of, or it's selected a different range of the data, and thus it's generated a different equation. So you can see with our previous equation, our highest error was 0.06%. Most of our error was actually really, really low. But let's use this new equation and see if we can improve our predictions. So again, I'm going to take these numbers. So in this case, it's 0.10 zeros because it's E negative 11 here, and then 5559. So let's type this in up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5559. And then our exponent in this case is 3.024. That number is really small, 3.024. And so that's updated our predictions here, and thus it's updated our error as well as our percent error. And you can see now our highest error is 0.05%, which is less than 0.06%. And another thing to notice is that our prediction of our imaginary kombucha sample is the same. So we've slightly improved the accuracy by excluding the 2% samples, but not drastically. So, you know, it's probably safe to say that we can, you know, Control Z, press Control and Z and go all the way back. Actually, I went back a little bit too far. But yeah, so the original equation that we had was pretty good. And you can look at the graph and see that, yeah, it is pretty good. It gets pretty close to this 2% sample. And, you know, an estimation of 1.85-ish for a 2% sample isn't too bad. You can also go the other way if you really want to. If for whatever reason you need to find higher alcohol content, then you can change the graph like that. And then if you use these new numbers, this time we have 5.299, E negative 12, so we're going to have 11 zeros. And then our exponent is 3.41. Let's type those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 5299, and 3.411. So now our prediction on the 2% samples is drastically improved. Look at that, 1.99. Remember before it was saying about 1.85. The error has increased on our 0.1% samples, and that's because our data set that we're looking at, again, is these higher alcohol percent samples. So it's going to be inherently less accurate on the lower percentages if you only include the data for the higher percentages. At the same time, it's more accurate on these higher percentages. So it's a bit of a give and take. So you want to use calibration standards in the range that you actually care about. Okay, so I've used Control-Z to go back to where we were before. Just wanted to mention a couple more things before I end this video. The first thing is your coefficient and your exponent. A lot of people get worried about the numbers that they get. So in my experience, the coefficient can vary from, you know, E negative 8 to about E negative 16. If your coefficient is more or less than that, then that's fine, as long as your data looks good. And then with the exponent, in my experience, the exponent is usually about 3 point something, sometimes 2 point something. But again, if you have an exponent that's a little bit larger or a little bit smaller, then and your data still fits, then that's fine. So don't get freaked out if you have strange numbers there, or rather I should say, don't get freaked out yet if you have strange numbers. If your graph looks good and your data points look good, then don't worry about it. So I just wanted to show the other two videos that are important to watch with this video. The first is this preparing standards alcohol detector video, and you can see my silly face right there. And then the second video is, of course, this accurate alcohol detection one, which shows you how to build the calibration curve in practice rather than just showing the Excel. Finally, this is really, really, really important. If you use Google Sheets, contact me and I will give you the Google Sheets version of this Excel document. Because if you try to import this Excel document into Google Sheets, it just completely breaks. The two programs just talk differently. So it's very important that you use the Google Sheets version if you're going to use Google Sheets. And you can see here, everything is pretty much the same. You still have E negative, a pretty large number, X raised to 3 point something or 2 point something. You still have your R-squared value to look at here. You still have your predictions and your error and your percent error. Your coefficient and your exponent are still up here, and your calculator is still down here. Again, if you're using Google Sheets, please don't import the Excel file into Google Sheets because it will completely break it and you'll get very inaccurate readings. So let me know if you need this Google Sheets document and I'll be more than happy to share it. So that's all I have for this video. Thanks for watching. Hopefully this has been helpful. If you have any questions, as always, feel free to email me or call me if you need to. And you can also leave comments in the description if you so choose. Thanks again. Have a good one. Bye.